Question number 11. This is a purely numerical question. A car of mass 1500 kg has a speed of 20 meters per second. So we have the initial speed, which is 20 meters per second. It accelerates until its speed is 25 meters per second. We have the final speed, which is 25 meters per second. We have not been given the time it takes to accelerate. The mass is 1500 kg. Let's read through. What is the increase in kinetic energy of the car? Okay, so we don't need the time given. Increase in kinetic energy, we just need to tell what is delta Ke, which is change in kinetic energy. So delta Ke would be final minus initial. The formula for kinetic energy is half mv square. So the final kinetic energy will be half mv square minus the initial kinetic energy will be half mu square, which I'll take the value half and m common, and then we do v square, which is 25 square, which is 625, and then we do u square, which is 20 square, so it's 400. This is equal to 168,750 joules, because the change in energy is also in joules. Now we can approximate this to 170 kilojoules. So the answer we have is C. Question number 12, a conceptual question. Which source of energy uses the production of steam to generate electrical energy? Okay, we will have to work through all of the options then. A says hydroelectricity. We know very well that hydroelectricity does not use steam, it directly uses flowing water. The flowing water rotates a turbine and that generates electricity. So we know for sure that A is not the answer. Option B says nuclear. This might be the answer because what happens inside the nuclear reactor is that nuclear fusion or fission takes place, which releases a lot of energy in the form of heat. This heat can be used to heat up water. Now this water gets converted into steam. The steam is high pressure, so the steam is used to rotate a turbine. And as it rotates a turbine, it generates electricity. So B is a possible solution. I'll star it. Option C says tides. The way tides are used is very similar to hydroelectricity. Water rises and then water falls, and the flowing water is used to rotate a turbine. So this is not our answer either because it has a similar process to hydroelectricity. D says waves. Okay, if we are talking about water waves, we know very well that it is the same thing as hydroelectricity. It will again rotate a turbine directly using the water. So this is also not our answer. Seems like we have got our answer and it is option B. A car traveling on a straight horizontal road has 1.6 million joules of kinetic energy. Okay, so the initial kinetic energy, I'll just call it IK, is equal to 1.6 million joules. So that is joules. Okay, now it accelerates for 20 seconds. So T equals 20 seconds until it has a kinetic energy of 2.5 million joules. Okay, so the final kinetic energy, I'll call it FK, is 2.5 million joules. So 2500 000 joules. We have been asked what is the average power output used to increase the kinetic energy of the car. Okay, what is the formula for power? Power equals work done upon time. So we have a change in energy. We have a change in energy. The change in energy is the work done. So we have delta Ke upon time. Now delta Ke will be equal to final kinetic energy minus initial kinetic energy. That is 2.5 million joules minus 1.6 million joules. and divided by 20 seconds. Now, using a calculator, we get 45,000 watts. I am using watts because it is joules divided by seconds. Okay, so 45,000 watts can also be converted to 45 kilowatts. So we have our answer and it is C. Question number 14. Which diagram shows an athlete exerting the least pressure on the ground? Okay, we are talking about pressure. Let's write the formula for pressure first. So P is equal to F divided by A. Over here, F is force and A is area. Now, what does it mean by area? Area is basically, so let's say in option C, the athlete is touching the ground only using his foot. So the area he's touching the ground with, that is what area over here means. So the area of the foot will be the area in this equation for option C. Okay, so let's just think about area because we are talking about pressure. In the first question, the athlete has one hand, a second hand like this, and then two legs. In option B, he has his whole body on the ground. So let's say this is his head, torso, and then also his legs. Very sorry for my bad drawing. In option C, we only have one of his foot. So it will just cover this much area. Option D, we have two of his foot. So it will cover this much area. Now we are talking about the least pressure. So as written over here, the formula for pressure is force divided by area. For all of the four options, the force we have is the same because it's the same athlete, his mass will be same and therefore the force he's applying on the ground will be same. F equals m into g. Therefore the only difference will be area in the four options. Now thinking about area, the higher area we have, the lower the pressure. Because of this formula, P is indirectly proportional to area. That's how fractions work. And therefore we need the highest area to get the lowest pressure. And seems like B is our answer because it has the highest area. Question number 15. We have been given a manometer. The manometer has three liquids. At the bottom it has mercury and on two sides it has liquid Y and liquid X. The diameter of the barometer is same throughout, as you can see in the main diagram in the question paper. Due to my bad drawing, we have a little more thickness over here, but we'll ignore that. Okay, so what do we need in the question? We need to tell how does the pressure compare between both the liquids and how does the density compare between both the liquids. Okay, so first of all, how does a manometer work? What a manometer does is that it basically measures the pressure or the force you have over this mercury over here. So if I had a larger force on this side, if this force, this arrow was larger than the force on this side, then it would mean that the mercury would go down. It would be somewhat here. But in the question, we have the mercury on equal level. That basically means is that the forces on this side and this side is the same. That also means that the pressure on this side and this side is exactly the same. Therefore, we can easily eliminate A and B because both A and B talk about the pressure being different for X and Y. The pressure for both the liquids will exactly be the same. I'll provide one more reasoning for it. We can see that there is a different height for these liquids. That means they have a different volume. One thing that might be of confusion to some people is that if they have different height, how they can have different pressure? How can they exert different pressure? The point is, we know very well that the force they exert over here is the same. Because if it was not the same, that the level will not be equal. Now pressure equals force upon area. The area we have over here is the cross-sectional area of the test tube, the area over here. The area is same for both, force is same for both, therefore pressure will also be same for both. So Px will be equal to Py for sure. Now, coming to the density part, which liquid has a higher density? Let's think about the volume first. So Y has a higher volume than X. So I'll just write Vy is greater than Vx. I'm sorry, Vy is smaller than Vx. Once we know that, let's think about their force. The force applied by both of these liquids will only depend on their masses. Okay, so what is the force applied by each of them? We know very well that the force they apply is same. So Fy equals Fx. Now let's use F equals ma. So this will become equal to m represents mass of y multiplied by gravity, acceleration due to gravity, equals mx multiplied by g. Both the g's cancel and we can see that mass of y is equal to mass of x for sure. Now let's think about density. What is the formula for density? The formula for density, I'll use d instead of rho here. The formula for density is equal to mass divided by volume. Over here both the masses are same, so we don't need to care about masses. The thing we need to care about are the volumes. Vx has a greater volume than Vy. That basically means that the fraction, the denominator will be greater for Vx. So what we need to compare is m, which is the mass for either of the liquids in the column, divided by Vx versus m divided by Vy. If we try to compare both of these liquids, we can easily say that this fraction over here, the first fraction is smaller because the denominator is greater. Therefore, the first fraction is smaller and the density of x is smaller than density of y. This is something which should come to you intuitively the next time you solve these types of questions. The first thing that should come to your mind is that they both apply the same force and therefore they will have the same mass because F equals mg as we see over here. And because they have the same mass, the liquid having the higher volume will always have the lesser density. And this is the reasoning for that. So therefore option C is wrong and option D is correct. Question number 16. Again a very conceptual question. Gas molecules exert a pressure when they collide with the walls of a container. Which statement is correct? Okay, so let's check through the statements here. Option A says they experience a change in force which exerts a pressure equal to momentum multiplied by area on the walls. Okay, so there is a delta F which represents the change in force and pressure is equal to, let's think about what happens when the molecules collide. So let's say this is one of the walls and a molecule comes like this and then goes back. I don't see a change in force over here. There is only one force that is directly exerted by the walls on the molecules and also by the molecules on the wall. So there is no change in force. So therefore option A seems wrong because there is no change in force. Yes, there is a change in momentum because the molecules change their direction. So option A is wrong. Option B says they experience a change in force. Again we have a delta F and therefore I can directly say this option is wrong. Now option C says they experience a change in momentum. So there is a delta momentum and pressure which exerts a pressure equals force multiplied by area. Force multiplied by area. This seems like a promising option because we talked about a change in momentum over here as molecules go from this direction to this direction. But we know very well the formula for pressure is P equals F by A, not F multiplied by A. So this option is also wrong. The correct option should be D. Let's check it. It says delta momentum which exerts a pressure equal to F by A. This represents both of the things we were talking about. There's a change in momentum because they change direction, and P equals to F by A. So option D is right. A thermometer has graduations which start at minus 10 degrees Celsius and end at 110 degrees Celsius. What is the lower fixed point and what is the upper fixed point of the Celsius scale? Okay, so we have a thermometer which has four markings, maybe more than four markings. After the figure, the question says what is the lower fixed point and what is the upper fixed point of the Celsius scale. Now over here we are not exactly talking about the thermometer, we are talking about the Celsius scale. So focus on the word Celsius scale. Now as soon as I think about the fixed points on the Celsius scale, I think about the boiling point of water and the melting point of ice. The reason is that is what a fixed point is. So those are the examples of fixed points. A fixed point is a point which can be easily reproduced universally. So if you are on sea level anywhere on earth, you will always see that the boiling point of water is always 100 degrees Celsius. So 100 degrees Celsius is always universally the boiling point of H2O, and the freezing point of water will always be 0 degrees Celsius. That's when it becomes ice. So these are the two fixed points that we talk about usually in the Celsius scale. Checking through the options, I think C should be the correct option because, well, these are the fixed points on the Celsius scale. Question number 18. A 1 kg block of aluminium requires more thermal energy to raise its temperature by 1 degree Celsius than a block of 1 kg of copper. This is something about specific heat capacity and in general heat capacity and latent heat. These are some of the topics that are related. If you want a session regarding these, if you found these difficult, you can always go to the website that is in the description and request a free session from one of our tutors. Okay, so let's move on to the question. The question asks, why does aluminum require more thermal energy? So option A says aluminum is a better conductor of thermal energy. This is not something we should be thinking about. The exact thing we should be thinking about is the heat capacity or the specific heat capacity. So I'll write SHC, specific heat capacity. What specific heat capacity directly means is the amount of heat required to raise a unit mass of a substance temperature by 1 degree Celsius. That is a mouthful, but that is exactly what we are talking about because we have 1 kg of a block of aluminium which requires some thermal energy to raise the temperature by 1 degree Celsius. That is what thermal heat capacity or specific heat capacity means. And we are comparing it to copper. So our answer should be that aluminium requires more heat because it has a higher heat capacity or specific heat capacity. Option A says it is a better conductor. We don't care about it being a conductor or not. So this is wrong. Option B says aluminium is a poor conductor of specific heat capacity of thermal energy than copper. I'm sorry. This is again wrong because we don't care about conductors. Option C says aluminum has a higher specific heat capacity than copper. This is exactly correct because that is what specific heat capacity is, the amount of energy required. So a higher specific heat capacity means that it will take more energy for aluminium to heat the same mass of aluminium. So 18 is correct. C is correct. Question number 19. Four campers are warming their food on a fire. They use different rods to hold their food near the fire. Which material is the best choice to prevent their hands from getting too hot? Okay, so we need to think about conduction here because basically, when they will hold their hands in front of the fire like this, if the material they are using is a better conductor, it will mean that heat will come to them more easily and therefore they'll burn their hands. Metals are usually the best conductors, so we should be aware of those options. Non-conductors would be a better solution in this problem. Let's check through the answers then. Option A says aluminium. This option is clearly wrong because it is a metal, it is a good conductor, and they'll burn their hands. Option B says copper. This again is a metal, maybe more conductive, maybe less conductive. We don't care. It is a metal. That means it is quite conductive. So this is also the wrong option because it will hurt your hand. Option C says steel. Yet again wrong. Steel is also a metal. Option D says wood. Now this is correct. Wood is a bad conductor of heat. Although the wood might burn a bit if we hold it for too long in the fire, but your hands will not get hurt. The four campers, any of those hands will not get hurt if they use wood. Therefore, option D is correct. Question number 20. We have two cans and one of them has a shiny silver outer surface. So it is shiny, silver colored. The other has dull black outer surface. So it is basically black, not shiny at all. Okay. They each have 300 grams of water at 80 degrees Celsius sealed inside them. They are both in a vacuum in the darkness of outer space. How does the temperature of the water in each one change? Okay. At the first glance of this question, the first thing that comes to my mind is that Cambridge is challenging us on two concepts over here. First is the change in temperature, so delta T due to the surroundings, and second is basically something related to radiation and how do waves flow. Okay, so first of all, we can see that we are talking about deep outer space. The temperature in outer space will be very low, maybe even lower than 0 degrees Celsius. That is something we know for a fact. So the temperature over here is very low in outer space. That will mean that heat will always try to escape. Heat will always try to escape from the can to the surroundings, which is vacuum. Therefore, the temperature will always go down. So delta T will always be negative inside the cans. Second thing we have is something related to radiations. There's something called black body radiation, which basically means that if a body is black and it is hot inside in outer space, then it will radiate away heat. So, and this heat will be in the form of IR rays. IR rays are a form of light and they basically carry heat. Just like light, they will be reflected back by shiny surfaces. So black body will try to throw away heat waves, IR waves. Whereas the shiny body over here, the shiny can over here will do something different. It will also try to throw back the rays. But the difference is that it has a shiny surface. That means that when the water will try to throw rays, some of the rays will be bounced back. If water tries to throw away rays, some will be bounced back, some may go through, some part of some others will may go through. So maybe this one over here, some part comes back and some goes away. But in general, it lessens the amount of radiation that goes away. So IR rays carrying heat is lessened in the case of the shiny body. Therefore, the temperature, the heat loss by the shiny body is lower. And therefore, I think the option C is correct because water in the shiny can cools more slowly as it is radiating away heat slower. This was a direct question about radiation and also a question about the change in temperature due to surroundings. Thank you. Always remember you can get a session on our website through our description.